We're going to talk about some specific forces that we're going to be playing with, and something that you should be familiar with for mechanics. All right? First one that we should be familiar with is weight. Weight is force due to gravity. Okay? So the force due to gravity is known as weight. And later on we'll talk about the normal force. Okay? And hopefully I can cover just these two for today, and then maybe we'll finish the other two later. So force due to gravity, or simply the weight force, well, we just know it as weight. Okay? Now force due to gravity is defined as F sub g. This subscript g represents force caused by gravity, and that is equal to ma sub g. So this a is acceleration due to gravity, and that is equal to mg. All right. Now g is acceleration due to gravity, and on Earth it is negative 9.8 meters per second squared y hat. So this works for pretty much anywhere on the surface of the Earth, right? Because even if you are in the southern hemisphere, like maybe even like Australia, right? Their down is still going to be pointing to the center of the Earth. So if you hold on to like a plumb bob, your plumb bob will show you the direction of your weight, right? So if you're a northern hemisphere, it'll go straight down, and even in Australia, it will go straight down for them as well.
Just a quick question: the honors videos, are they just MP3 files, or what? I have a
They are.
Missed the number. How can I get her to watch them? Are they in the shared folder? Can I copy
They
them?
are in the shared folder.
Can I copy them into?
Yeah, you should be. You should be able to drag right over. And I uploaded it on Schoology YouTube, so you could.
But you have like an index link or something for it?
I could send you the link as well.
Well, for right now, I'll just put the videos.
Yeah.
Sorry.
No problem.
I told you, you're too far ahead. Speak slowly.
So,
There you go. Good.
Earth, round, not flat. So the direction of G will always be towards the center of the Earth. Okay, just keep that in mind. Now, depending on which planet you're on, your acceleration due to gravitational pull by that planet will be different. On Earth, again, is negative 9.8 meters per second square y hat. But on the moon, let's say, it's not as massive as the Earth. And on the moon, the acceleration due to gravity on the surface of the moon is negative 1.67 meters per second squared y hat. All right? On Mars, it's like 3 something, right? Jupiter is like 10 something, almost 11, So it's all different depending on where you are. Okay? So the direction, okay, the weight force, right, will always be towards the center of the Earth, okay? Okay? And that is the negative y hat direction, okay? So, force due to gravity acts straight down, even if the mass is on an incline, okay? So if we were to actually have, like, I don't know, something like, okay, and let's say we have an object, okay, resting on the surface like this, horizontal surface. Okay? Well, this will give me weight that is straight down, okay? And that's pretty easy to see, okay? And so if this thing is actually on the horizontal surface, our weight will be straight down. It's really that simple, okay? And that weight is simply F sub g, and that is equal to m times g. Okay? Even if it's on an incline like this, okay, on a tilted plane, on an incline like this, it doesn't matter what the angle of this incline is. Your FG will always be straight down, as though if you are holding your plumb bobs, and then plumb bob will always seek down. And even if you are having this on a ceiling, let's say, it will still be straight down, okay? There's no negotiation on that, okay? It will always be straight down. Easy enough? Yeah. Well, just saying that that is the surface. That's all it means. Really. So you know where that solid surface is. The next thing we're going to talk about is the normal force. Okay? The normal force, we sort of brushed it by earlier, but I think it's important to understand what this normal force is. This normal force, okay, of a table or wall or ground must be at 90 degrees to the surface. And that means that mathematically normal, okay, mathematically normal. So it is perpendicular to the surface, right? You could also think of it as a supporting force, right? Right? By the surface. Okay? So here, if I have a box, an object on a horizontal, I guess it could be a floor, or it could be a surface of a table, or, all right, horizontal surface, okay. I have two forces acting on this object vertically, okay. Obviously, the force that is pointing straight down is my FG, okay. This is my FG. And my Fg is equal to m times g. My other force acting on this object is the supporting force on this object by this surface, which is called the normal force. And this is the normal force right here. We will consider up direction positive in this case, and we're going to consider the down direction to be negative. Okay? So, if we were to think about this and apply Newton's second law that we learned, okay, we can say that sum of all forces in the y direction is equal to ma y. This is Newton's second law. okay? Because we're only looking in the y direction. Then, by definition of the net force, sum of all forces in y direction is simply just adding up all the forces. There are only two forces here. One is the F normal plus Fg. Well, since these two are identical to each other, that means I can set these two equal to each other as well. So I can say now m times a sub y is equal to, right, F normal plus Fg. Now these are all vectors now, okay? So now I'm going to give directions to all this. Well, first of all, is this object accelerating in the y direction? Is it like levitating off the surface, or is it going through the surface? And the answer is no. So my acceleration is 0. So the whole left side of the equal sign is 0. F normal, is that positive or negative? That's definitely positive. So I'm going to leave that as F normal as positive. Plus Fg, what's my Fg? Is negative. Now notice how I took off the vector symbols now. Now I gave directions to this. Okay? So if I solve for F normal, my F normal in this particular case is equal to simply Fg. Okay? Or you could simply say, in this particular instance, my normal force is same as the weight. However, this is not always the case. Okay? This is not always the case. Because let's say I have these three different scenarios. Okay? Here, let's say I have a box, and this box has mass of, let's say, 10 kilograms. All right? So the mass of this box, 10 kilograms. Okay, so this is the mass of the box. If I look at this, there are two forces acting on this box, right? One is always the obvious force, which is Fg. You cannot escape Fg, okay? Fg will always be present. And Fg is simply m times g. In our case, it is simply 10 times 9.8. Now, I did not put any vector symbols on this. I'm just working with scalar quantities, okay? So my Fg is equal to 98 newtons. I have another force acting on this object, and that is from the surface, acting on this box by the surface, and that is my F normal. Okay? So my F normal is simply acting on this object from the surface, right? On surface by, no, on object by surface. So here's my F normal. So when I only have these two forces acting on this object vertically, my F normal is simply that. My F normal is simply mg, okay, is equal to mg, which happens to be simply 98 newtons. So that's easy. So someone may say, well, then isn't like just F normal always the same as the weight? And the answer is no. Because F normal is a reactive force, not proactive. What if I have an extra force acting on this object vertically? So for example, here I have FG again, acting straight down. Oops. Crap, I made it a little too long. Sorry. So I'm going to make this FG. Okay? FG. And we already know what that FG is. Just FG is 98 newtons. Okay? And I have F normal going straight up. But, well, I'm going to make it a little longer for this one. And I have another force that is actually pushing down on this. So F push. And this F push, downward direction of 50 newtons, let's say. Now, if I push down on this with FG going down, what do you think is going to happen to my F normal? It should be up, higher, more, right? More than 98. Well, let's see if that's true. Let's see if we can calculate that. Okay? So again, I'm going to start by saying, okay, sum of all forces in Y is equal to MAY. And then sum of all forces in Y is equal to, it looks like I have F normal plus FG plus F push. I can set these equal to each other and saying MAY is equal to simply F normal plus FG plus F push. Now give directions. So my acceleration, again in y direction for this object is 0, because it's not going to be levitating off the ground, or it's not going to go through the ground. F normal, positive or negative? It's definitely positive. Plus FG. FG is negative. Plus F push. Negative. So if I solve for F normal by bringing these two to the other side of the equal sign and flipping it, my F normal just becomes FG plus F push. So my F normal is equal to 98 plus 50 newtons. So my F normal now is equal to 148 newtons for my F normal. So it's not the same as the weight. Okay? Let's say I have another scenario. So here, again, I have my FG. Here's my FG acting straight down. Okay? Here's my FG. And this time, let's say I am pulling it up a little bit instead of pushing down. Let's say I'm pulling it up. So here is my F pull. And let's say my F pull is 50 newtons. What's going to happen to my F normal now? It should decrease than my weight, right? So my F normal is going to be somewhere like this. Okay. So here's my F normal. Okay. So if I work this out, I know most of you can do this in your head, but I'm showing you these 4 steps, which is very, very important. And I want you to always give me these 4 steps every time you solve dynamic problems. Alright? So sum of all forces in y again is equal to MAY. And sum of all forces in y is equal to, again, we have F normal, right, plus FG plus F pull, right? Now, when I set them equal to each other, MAY is equal to all this mess, right? F normal plus, right, plus FG plus F pull. Now give directions. Again, my acceleration in the y direction is 0 because it's not going to be levitating off the ground, or it's not going to be, all right, going through the ground. So 0 is equal to F normal, positive or negative? Positive. FG, negative. F pull, positive. Therefore, if I were to now solve for F normal, my F normal now is equal to simply FG minus F pull, which is, my F normal now is equal to 98 minus 50, so my F normal becomes 48 newtons. So it's not always same as the weight. Okay? So what happens when we actually place an object instead of on a flat horizontal surface? What if we place it on an incline like this? Okay? Well, F normal always acts perpendicular to the surface, even if the mass is on an incline. So this is my F normal right here. Okay? It's perpendicular to the surface. So this here is 90 degrees. Okay? So if I were to extend this incline straight out, this is my angle theta for my incline. Now, to solve something like this, what you really need to do is, you need to do this. Ready? Dun dun dun. This is your new x-axis. So I'm going to say this is your new x-axis. And this is your new y-axis. Okay? Therefore, this FG right here, this FG, which is equal to mg, becomes the hypotenuse of your xgx, the component this way. Now notice the arrow of my FGX. It is always pointing down the incline. That's my FGX, which is the x component of my FG. And this is my FGY. Notice the arrowhead of my FGY. What is this angle right here? This is definitely 90 degrees. What is this angle right here? That is theta. That is correct. And how did Noah get that? Well, he guessed correctly. Well, let's take a look. If I were to extend this FG straight down, this is right angle then. Yes? Then this is complementary angle of theta, right? Well, if this is complementary angle of theta and this is a right angle, then this has to be theta. So we proved it. So now we can use it. So here, my FGX is now simply the opposite component, which is FG times what? Opposite component of my angle theta, which is sine theta. So if you don't pay attention, you're going to get screwed. X sine. For this one, FG times, this is the adjacent component to my angle theta. Therefore, it is cosine. This FG sine theta can also be described as F parallel, and FG cosine theta, or FGY, is sometimes described as F perpendicular. So, if I were to use this like that and just do the y's, sum of all forces in y's, what would my F normal be? FGY. Because there are no other vertical forces acting on this. Yes?
The FGX deceleration down the slide.
Well, what do you think is going to happen to FGX? What's going to happen to this object? It will slide down. How? At a constant speed? It should accelerate down. What would happen to that acceleration as this theta grows? You should get faster. When this theta reaches 90, what should your acceleration be? 9.8, right? Now what if I made this thing on an incline and it didn't slide? Yeah, and we're going to talk about that next week. I'm not going to do that today. All right, very good. All right, I'll stop there for as far as this is concerned. Now,